open sets are protective sets, what are going to be the closed sets? So the very first definition seems not ominous at all. A set is closed if the complement is open. Definition. So you might say F, which is a subset of the metric MD, is closed. And you understand closed in M, obviously, it's relative. If, and that's if and only if you prefer, if and only if F complement, which is simply the elements of M minus F, is open. So closed means that the complement is open. So what does it mean? It means that if X belongs to, if X does not belong to F, X belongs to F complement, and that means that X is staying far away from F. X is protected against this F. There exists a ball of radius r around X that is wholly contained in F complement, right? In other words, this guy is somewhat far from X. He's not in contact. Sorry, he's not in contact with the F. F, by the way, from the word fermé, if you know French. Fermé. Where is he when you need him? Fermé. So this is our characterization of the set. Seems not scary. What does it mean? Think about what this means. So the only elements that are not part of a closed set are those that are able to stay clear away from that set. So the image of closed sets that you get is something like this if you watch the horror movie The Blob. See? This X is having quite a lot of trouble because, you see, look at it, no matter what neighborhood you select around him, he is not protected. He cannot be protected against F. He is not part of the complement, and therefore it must be part of F. If it touches you, it eats you. Yes? If it touches you, it eats you, which brings me, let's see, to the following question. Another horror movie. So what you have here is, zombies have invaded the earth, and you see a bunch of them, and then you aim with your rifle and at the head of your friend because he's surrounded by zombies. Do you shoot? I guess weird question from someone like me, right? Do you understand what I'm asking? Okay, so F or Z is the set of all zombies. Is the set of all zombies a closed set? What do you think? Do you understand the definition? What I'm saying is a set is closed if the complement is open, which means the points that are not part of the set are those points which are separated by some distance from any members of the set F. So if the set F were the set of zombies, is this a closed set? Do you see what I'm asking you? The blob. You understood the analogy of the blob. Why is a blob a closed set? Because anything that comes in contact with this 1950s, the blob, is going to be part of the blob. Right? The only things that are safe are things that are surrounded by a bubble, so the blob cannot approach them. They're in the complement, surrounded by the bubble. The blob cannot approach them. So, what do the zombies have to do with it?
Are you trying to say that the zombies would then eat anyone that touches them and turn them into the zombies?
Exactly! You got me.
Okay.
Generation Y, dang.
You understand what I'm saying, right? So here, you aim at someone, either the member you aim at is a zombie, or the member you aim at is clear away from them, so they will be standing here, and there is definitely an open ball. This scope is an open ball. You can see that he's not surrounded. There is some chance, right? But in this case, no matter how small is the circle, zombies are already there. They're right there. So if you kind of don't consider the time, he is a zombie. So zombie is another example of a closed set. You see, so they are a set of horror movies. Let's look at examples. So you understand the difference, right? So open sets are protective sets. They are things that protect against bad things. They are like charms. So if you read Gogol's V, what does he do? Gogol's V, he has to be, it's like a horror story, pretty nice. So he's a monk, and he has to read for 3 nights prayers for a beautiful maiden that has died. She's a member of a chieftain. Okay, so basically each night as he reads, she wakes up from the grave and she tries to get him. What does he do to protect himself? He draws a circle around himself, and she cannot get in the circle. Why? Because he has created an open set to protect himself. Okay? At the end, of course, he got afraid, and the open set did not work. Maybe he didn't fully close the ball. Okay? So there are plenty of horror stories that you can see that the evil carnivorous creatures are really the closed sets, and the open sets are protecting against them. So, does it make sense? It's just right from this definition. The only guys that are protected are the ones that are not touched. Sorry?
To make like a number line analogy, if we have the set from the open set from 1 to 2.
The open set from 1 to 2.
The closed set from 1 to 2.
Right.
Then if we take the complement, 1 isn't included in that.
Well, if it's a close from 1 to 2, 1 has to be included. The complement is everything protected. So again, maybe it's premature. I just want to see an emotional reaction from you. You look at me like this, right?
Like
I feel
zombies.
all is gone. Everything is lost. So what about the empty set, right? Empty set and M. Are they closed sets? We saw that the empty set is open. Do you agree? The empty set is open. Why? Because if you pick any member of the empty set, he is protected against the complement. Why? Because there is nothing to pick. There is nothing to protect, so automatically there is, in other words, show me a member in this empty set that is not protected. Since you cannot do it, automatically you have to conclude it's open. This is M, and M is open. Why? Because pick any point X and draw a ball of any radius. Automatically that ball only contains members of M. By default, because balls are defined as subsets of M. So M automatically is open. But what about being closed? Is this closed? Is the empty set closed? But the definition is, we know it's closed if the complement is open. What's the complement of the empty set?
Everything.
Everything, namely M. The complement of the empty set is M. And M is open, so empty set is closed. So let's write like that. So they are always closed. because the complement of the empty set is M, which is open, and the complement of M is the empty set, which is also open. So you understand what I'm saying? So because I take the complement of the empty set and I get an open set, that means the empty set is closed. Because when I take the complement of M, I get an open set. M is open. So M is simultaneously closed and open. Sometimes you say open.
Will there be other examples of sets that are both open and closed simultaneously?
Yes, they will be. So the word open and closed might give you the wrong idea. You understand what an open set is? An open set is one that protects the members, right? What is a closed set? A closed set, viscerally, is one that when he grabs something, he eats it. So it, of course, it might protect its members, but yet touch anything and it will eat it. Okay? Because you see, that follows from this innocuous definition. It doesn't look scary, so you might kind of make a horror movie. The scientists, they didn't know what they were doing. They just made this innocent definition, and yet here's what happens. Okay? So let's consider other subsets. Let's suppose we have, I'm just gathering things that are obvious about closed sets. Later we'll give more specific characterization. So B, what about an arbitrary intersection of closed sets? An arbitrary intersection of closed sets is closed. This follows why? Remember with open sets, arbitrary union of open is open, but arbitrary intersection of open sets isn't necessarily open. Okay, so how do we know? What we can do is this. So let F be equal to some arbitrary intersection of F alpha. And here I'm saying that each F alpha is closed. Now, how do we verify that this guy is closed? All we do, we take the complement, and if the complement happens to be open, that's all we need. Then, F complement, by the Morgan laws, right? If I take the complement of a union, or complement of an intersection in this case, that would be what? That will be the union over alpha of each F alpha complement. Okay? So if it's not, if it's not in the intersection, it means it's not in one of the sets that you're intersecting. So it's in the union of this, which is open. Therefore, F is closed. Yes? So, C. What I'm now claiming is that any finite set is closed. Okay, any finite set is closed. Why is this the case? So let's consider when you only have one element. So let's consider F equal to X. Only one element in F, okay? Is this set going to be closed? Well, let's see. What we need to do is to show that F complement is open. But if you have M, so here's the picture that you have here. So if this is your space M, and you pick this X, so this X is not part of the set. So U is this M, this F complement is the set M where I punctured out X. I just removed it. Everything else in the square is part of the F complement set, right? So then what I do is if I pick some point Y belonging to F complement, F complement is equal to M minus the point x. Okay? So let's pick y in that set. If I pick y in that set, here it is, I need to create an open ball centered at y that does not contain x. How do I do this? Well, y is not x, so there is a non-empty distance. Here it is. So, and I use this distance to insulate myself from x. So this distance is so I pick epsilon equal to the distance between x and y. And then what we have is that the ball of radius epsilon around y will be a subset of f complement. Okay, so I can always, right? For another point, I pick a different distance, and I use that distance as to generate my radius for the open ball. Make sense? So that implies that f complement is open. Now, what about if I have more points? Now, what I can say is that any finite union, it's a finite union of closed sets, is closed. Why do I know that? Is because if I take f and I write it as union k equal 1 to n of f sub k, where those are closed sets, then I can take the complement. F complement will simply be the complement of this union. But taking the complement of the union, it's like the intersection of the complements by the Morgan law. Yeah? And this is a finite intersection of open sets. Which is therefore open, which implies f is closed. Yes?
In B, isn't f complement bigger than the union of f alpha complement?
No, so here, f is, so that's B, right? So f is the intersection of f alphas.
Yeah.
Okay? So if I take the complement of this set, I take the complement of this intersection. Now, what does it mean not to belong in this intersection? It means that an element that doesn't belong in the intersection it either doesn't belong to one of the f alphas or another f alpha. In other words, it doesn't belong to one of the f alphas, which means it is the union. This and that are the same.
If it's in the complement of the intersection, it can still be in one of the f alphas, right?
Well, so if it's in the complement of the intersection, it could be in one of the alphas, but it will be in this union. And if it's in the union, it's in the intersection. So if in the complement of the intersection. Okay, so think about it. You can justify it by just selecting a point in here and showing it's in here, and vice versa. But you can even do that by logic. So what is this? This means an element that does not belong to this intersection doesn't belong to one of the f alphas. So it belongs to one of the f alpha complements, and therefore belongs to the union of such f alphas. Now, if something is in the union of those f alpha complements, it means it's in one of such f alpha complements. Okay? And therefore, it is not in one of the sets that is being intersected, and therefore in the complement. So you can kind of write it out, or reason it out. This is the Morgan laws, and that's always true. Complement of an intersection of sets, arbitrary intersection, is the union of the complements, and vice versa. So so this was what? So you understand? So any finite union of closed sets is closed. So what can I do? So now if my f is a finite set, like x1, x2, xn. Now I can write f as x1 union x2 union all the way to xn. So that's a finite union of closed sets. We showed that a singleton, by this argument, singleton is closed, so a finite union of singletons, by this argument, is also closed. You're itching to leave. Goodbye.